last time we stopped at the ionic bonding as the first type of a chemical interaction between atoms of different elements. And we said that the reason or the driving force for any type of bonding between elements is the need for each atom to reach as much stabilization as possible or have as lower of energy as possible. So all the atoms are trying to minimize their energy or stabilize themselves by gaining the electronic configuration of a noble gas. And that can be achieved in case of the ionic bonding by losing electrons for metals and gaining electrons for non-metals. And it's going to be possible for this to take place if you combine metals with non-metals, because metals favor losing electrons and non-metals favor gaining electrons. So it's for the benefit of both of them. If we combine atom A with atom B, and A and B are metals and non-metals, A prefers losing an electron and B prefers gaining the electron. So a complete electron transfer will take place and you will get a positive ion for A combined with a negative ion for B. That's an ionic combination or an ionic bonding. But if you have a combination of A and B and both are non-metals, so both are actually preferring to gain electrons, so there will not be a driving force for a complete transfer of an electron. So what will happen is that A and B will share electrons, and as a result these sharing electrons will be counting towards the electronic configuration of both of them equally. So it will be a way to complete their electronic configuration to reach the most stable configuration, which is the configuration for a noble gas. And it usually corresponds with 8 valence electrons in the valence shell. That's why we have the octet rule, which means all the atoms in a covalent bond are trying to reach an electron count in the valence shell that equals 8, because that corresponds to the electron configuration of a noble gas. So, for example, when you combine 2 fluorine atoms together, those are non-metals. They're actually equal. There will not be a chance for an electron transfer from one to the other. Actually, what determines if an electron transfer will take place or not is electronegativity. So in this case, for ionic bonding, it's a very small electronegativity for A, and it's a very large electronegativity for B. That's why B is able to strongly attract the electron and kind of completely transfer it from A. And there will be a threshold for whether the electronegativity is going to be strong enough for a complete transfer or not, which is that the difference in electronegativity between both atoms has to be greater than 1.9. Okay, so if it's greater than 1.9, you will have ionic bonding. If it's less than 1.9, you will have a covalent bonding. So in case you don't have a strong difference in electronegativity and a complete electron transfer is not possible, they will simply try to satisfy the stabilization of the noble gas configuration by sharing electrons together. So that fluorine will share electron with that one right here. And as a result, if you carefully check, you will find that the number of valence electrons for each one of them changed from 7 to 8. So 8 in the first one and 8 in the second one. Okay, so it changed from a partially filled orbital or valence shell to a completely filled valence shell that corresponds to a noble gas configuration, which is going to be much more stable. Okay, And in this context, you will find that there are two types of electrons in this situation here. Electrons that completely belong to one atom or the other, so it's not shared, and those are called lone pairs. And that single pair in the middle is going to be completely different. It's shared between both of them, and it actually constitutes for the bonding pair or the covalent bond that bound the two atoms together. And just to differentiate this electron pair from the other lone pairs, we'll just replace the dots with a dashed line, just to represent that this is a different bond, this is a different pair that forms the actual bond between the two atoms and holds them together. That here is the single bond between the two atoms that holds the molecule together, and those are the lone pairs. And the whole thing here is called Lewis structure. So that's the easiest description for a covalent bonding in any molecule. As you can see, it gives you really interesting information. It tells you how many atoms in the molecule. It tells you what or how many bonds are forming between the two atoms in that molecule. And it tells you how many lone pairs are around each of the atoms. So it tells you a lot of useful information, and we'll learn a little bit more as we go forward in the discussion. That same description here is very useful to describe any molecular species, any covalent compound. So if you try to draw the Lewis structure for something that is even higher nuclearity, more than 2 atoms, 3 atoms, 4 atoms, 5 atoms, 10 atoms, it's going to be the same thing. In all cases, you will represent the valence electrons of each atom as dots, and then try to see what will happen when they share electrons with each other in order to satisfy the octet rule for each atom separately. So in case of water, you will have 2 hydrogen atoms, each one have 1 electron, valence electron, and then an oxygen atom with 6 valence electrons. For the hydrogen, it only needs 2 valence electrons to have a complete configuration that corresponds to helium. So it needs to share 1 electron with one other atom. For the oxygen, it has 6, which is 2 electrons away, and that's why it needs to interact with 2 hydrogen, not just 1, because it needs 2 more electrons to have the or to satisfy the octet rule. So once this interaction or this sharing happens, this is what will be the result. That hydrogen here will share the electron with this side, and that hydrogen will share electron with this side. And as a result, you'll have oxygen with 8 electrons around it, so it satisfies the octet rule, and hydrogens with 2 electrons around it, which is what it is needed for the hydrogen. The octet rule for hydrogen is actually 2, not 8. Okay, and that's the same thing for the second hydrogen. And as we said, we replace the bonding pairs with lines and leave the lone pairs as dots to just differentiate between them. So that here is the Lewis structure that tells you that it's 2 single bonds between hydrogens and oxygens, and the oxygen is in the middle. In some cases, when you do the Lewis structure for a compound, one atom might need to form more than 1 single bond with the same second atom. So in that case, it will be multiple bonds, like double bonds, 2 bonds. That is the case for carbon dioxide. In all cases, it is however number of bonds needed for the atoms to fulfill the octet rule, to have a total of 8 electrons in the valence shell. So you can see here for the carbon dioxide situation, oxygen needs to form 2 bonds with carbon in order to have 8 electrons. And same thing for the second oxygen. And it's the same thing for the middle carbon atom as well. It might even be 3 bonds that are needed for an octet rule satisfaction. That's the case for nitrogen, for example. So it needs 3 bonds to 3 electrons to be shared between the 2 nitrogen atoms just to reach the octet rule 8 electrons in the valence shell of both of them. Okay? But one thing before we discuss drawing law structure for different molecules is actually trying to imagine how that sharing physically take place. What happens here is that the orbital, the valence orbital of atom 1 approaches the valence orbital of atom 2. So what happens when the 2 atoms move closer to each other? When they are away from each other, they're not interacting. But what happens is that when they move closer to each other, the nucleus of atom 1 will attract the electron cloud of atom 2. And the nucleus of atom 2 will attract the electron cloud of atom 1. So that's an attraction force that will cause them to move even closer. And since it's an attraction force, it's actually lowering the energy of the system. So as they get closer, the energy will keep going down and down further. Okay? At one point, when they get too much closer to each other, the nucleus of atom 1 and the nucleus for atom 2 will be too close that they will start repelling each other. So that repulsion force is going to increase the energy of the system. So once this repulsion force is strong enough, it's going to start increasing the energy of the system, preventing the nuclei from coming even closer from each other. There will be an equilibrium position between the repulsion force of the nuclei and the attraction force of the electrons. That position here is actually the exact distance of the bond. So that defines the bond length in that case. And whatever amount of energy stabilization takes place at this equilibrium position is going to be the energy of the bond, or how strong the bond is. So the more the energy stabilization, the stronger the bond will be, and the less, the weaker the bond will be. So for any bond, we need to define 2 parameters: the bond energy, which is a direct correlation for the strength of the bond. It's how much energy released when the bond forms, and the bond length, which is the distance between the 2 nuclei of the 2 atoms forming the bond in that molecule. The length as the first thing is gonna depend on 2 things. It's gonna depend first on the size of the atoms involved. So of course, when you think about the bond between 2 hydrogen atoms, it's gonna be significantly smaller than the bond between a hydrogen and an iodine, because iodine is significantly larger to start with. So that will make the distance between the nuclei significantly larger. So that's the first parameter here. Second parameter that determines the length, if you are comparing 2 atoms of the same nature with more and more number of bonds. The more number of bonds, the stronger the attraction will be, which means the shorter the length will be. So the longest bond is going to be the single bond, and then double bond is going to be shorter, triple bond is going to be shorter. So, and that's clear from this table right here. If you compare something like single carbon-carbon bond to a double bond, it's going to be shorter. A triple bond is going to be even shorter.
Can I say something?
Yes, sure.
A way that I kind of remember this is if you think about it as a rubber band, kind of.
Yes, that's a good analogy. It's kind of something that like causes the objects to come closer to each other, so force it towards each other. So the more attraction, the closer they will get to each other. So if you have, as you said, if you think of it as a rubber band, if you have one rubber band is gonna hold it at a certain distance. If you put more rubber bands, it's gonna force it even closer as you increase the number of rubber bands. Let's think about this question here. So which of these compounds here will have the longest bond lengths? And that's a clicker question. So just remember, we talked about the two parameters that affect the bond lengths. First one is the size, and the second one is the bond order, number of bonds. Okay.
Wait, I'm kind of confused on the bond order.
It's just the number of bonds, as we said. As you said, the rubber band analogy: single bond, one rubber band; double bond, two; triple bond, three.
All of these would have a single bond, right?
Yes, that's a good thing to note here.
So then, do I just look at which one has the highest, like which one's the biggest, basically?
Exactly.
Okay.
Bond order is not a factor here because all of them have a single bond, right? So the only difference is going to be the size of the atom involved in that molecule. So as you know, if you remember last lecture, when we discussed the size, as you go from fluorine to iodine, is going to be an increasing size. Size increases as you go from fluorine to iodine because they're actually put in the same order as they are in the periodic table. Hydrogen is the same size, so the size of fluorine to iodine or of the halogen is going to be the determining factor here. And since the size goes larger downwards, it means the bond length is also increasing in the same direction. So that is going to be the longest bond in all of these combinations. What about which one will have the highest bond energy, the strongest bond energy?
Would it be the first one?
What's the argument here?
Because it has the highest molar mass.
The first one has the highest molar mass.
Couldn't you also use Coulomb's law on this? And since
exactly, thank
the
you.
radius between them are the smallest.
Exactly, thank you. So the bond energy is an attraction force that is proportional to the charge, inversely proportional to the square of the distance. Distance is the bond length. So if the bond length goes smaller, the force or the strength goes higher, right? So shorter bond length means stronger attraction and vice versa. We just said this a couple of minutes ago. When you have a stronger attraction, that will cause the bond length to be shorter and vice versa. If you have a shorter bond length, that means you have a stronger attraction.